We are going into the concept development stage and functional analysis, material that is covered in chapter 7 of your textbook. And this is the agenda. So we're going to start with the system concept or selecting the system concept. So if you, and based on what I saw in the exam, we all remember the system lifecycle model. You did very well in that question. So now we are transitioning from this needs analysis portion into the next phases where the new ideas and concepts are developed to the functional analysis phase, where the new system concept starts to be engineered, right? So we're going to be using functions to describe the system activities, the interactions, and the operations, and those are created here. We as systems engineers, we have several tools to create these products during this phase. And that basically is going to lay out the foundation for what our system is going to look like. So this concept definition phase of the system lifecycle marks the beginning to define the functional and physical characteristics of a new system, right? So up to this point, we've been conceptualizing what the system must do, what are the goals of the system, what are the things that the system must meet in terms of requirements. From this point on, now we get to engineer how to achieve those goals. It marks a commitment to characterize the system in sufficient detail to enable its operational performance, right? So it's not just measuring, but now we want to make sure that we arrive to that performance, the time it's going to take for us to complete the development, and the cost that is going to be needed, or the amount of resources that we're going to need in order to achieve this development. So for us as an output, we want to select from a number of alternatives a concept, right? So after completing this phase, basically we're going to have options, and then but using what we know in terms of trade-off analysis that we have covered already, we're going to try to shoot for the best system, not the optimal system, but the best system that balance out our time, our schedule, our performance, and the cost. So this is where we are right now. We are in the concept definition phase in the system life cycle. So we are right here. And for this particular phase, the inputs are the system performance requirements, which we have defined already in the needs analysis. The technology base that includes a number of feasible concepts, and the contractual and organizational framework in which the system development is going to be cast. So as you can see, we are in this concept definition phase in the system lifecycle. So when we talk about the inputs, we are talking about these performance requirements that we defined in a previous lecture, and also having some candidate system concepts in terms of visualizing, okay, these are the potential subsystems, and this is how they're going to be integrated. The outputs are the system functional specifications, one concept that is going to be moving forward, and a detailed plan for ensuring the engineering program. Okay, so as you can see from concept definition, we are going to go into the advanced development. So in order for us to move to that phase, we need to have one good concept that we have agreed to move on for development. So the planning outputs of this phase are usually specified to include the Systems Engineering Management Plan, or SEMP, which defines in detail the systems engineering approach to be followed, the project work breakdown structure, the cost estimates for development and production, the testing plans, and other supporting materials as might be directed and you can refer to lecture 4, in which we discuss what's the NCMP, what is the work breakdown structure, and so on. Going back into the design materialization status, so far we have looked into the hierarchy of the system, right? Subsystems, component, subcomponent, and part. So we are already looking to the needs analysis, the concept exploration. Now we are in this phase in which we are looking at the definition of our concept. So at the system level, we are going to define selected concept with specifications, right? So we are going to have a specific concept that is going to be moving forward, and we are going to define functional and physical architecture for that concept. And then we are also going to start looking at the component level, start to allocate some of those functions for our concept to specific technology. So in the concept definition phase, the design focus is on components, the fundamental building blocks of the systems, as we discussed already. In this phase, again, we are focusing on the selection and functional definition of the system components and the definition of their configuration into subsystems. The performance of the above tasks at this level or at this phase are a primary responsibility of the systems engineer. And as we've been doing for the other two, like we did for needs analysis or for concept exploration, we had to take this into our engineering method or the systems engineering method at this phase. And these 4 steps are applied as follows. First, for the performance requirement analysis, some of the activities that we are going to be performing at this phase is to analyze the system performance requirements and relating them to operational objectives and to the entire life cycle scenario. So we start kind of mapping all the things that we have started to do in the previous phases. We are also going to refine the requirements as necessary to include unstated constraints. So as we start comparing these different concepts, we can start realizing that there's some pieces that were not necessarily described in our requirements. So we might need to add more to our requirement definition. In terms of function analysis and formulation, we start allocating subsystem functions to the component level. So far we've been thinking about, okay, this is the system that I want to deliver at the end. And these are based on my initial definition of the goals and performance that I want to achieve. These are the subsystem that I'm envisioning for my system. Now we start looking at the functions and we start allocating those subsystem functions to the component level. Right, so if you remember one of the exercises that we did, I'll say like 2 or 3 weeks ago, was to start defining functions for different type of systems. That's the type of exercise that we are going to perform for your project. But now we're getting into the next layer, right? It's not only the functions that each subsystem must perform, but also the functions from that subsystem. We start allocating those functions now into the component level. We start looking at developing the functional architecture for the product and formulating functional requirements corresponding to the assigned functions to those components. Then we move to the concept selection. Right, so we start by synthesizing alternative technological approaches and component configurations designed to performance requirements. So basically what we're trying to do now, let's say originally we have a concept. Let's say we are trying to define a new system for transportation system for students at Texas State University, right? So we want to make want to make sure, like, as we keep growing, we are 40,000 students now on campus. Maybe in 10 years, there will be 60,000 students in campus. So there will be a problem. How do you move people from one side of campus to the other side of campus? So that's, let's say that's our problem. That's the system that we want to design. So how do we move people from, let's say, from Strahan Coliseum to Ingram School of Engineering without having to use a school bus, right? Because maybe traffic is gonna be so bad that driving from that location to this location could take 30 minutes. So we start thinking about, okay, so what are the, so I'm going to address transportation on campus. Right, and I specifically want to make sure that students are able to park and get to their classes on time without having to spend 45 minutes to try to find a parking spot close by. Okay, so what are the things that we need to achieve that? Maybe at this point, the concept exploration phase, we were looking at different subsystems that might help in terms, maybe there could be an app, or that's the solution. Let's talk about a subsystem that provides real-time information. Real-time information. Another subsystem that that has route data. Another subsystem that is the actual implementation of, let's say, transportation links.
Or route data go in real-time information?
Well, real-time information could be like traffic information. Route data could be, okay, these are different routes that you can take to get to the location that you are shooting for, right? Well, yeah, I mean, it could be associated. I'm just making this example right now, but yeah, that can be linked. For now, let's just keep them separate. The other subsystem may be, I don't know, moving, or I don't want to call it transportation because it's gonna be redundant. Say physical,
where the stops are, maybe?
Yeah, the what?
Where each stop is?
Yes, so
the location.
each location or stops or locations, right?
Vehicle types we can use.
Or stops. All right, and mediums, right? Like, what are the transportation mediums that you're gonna be using? So those are probably 2 core subsystems that you can start addressing on this concept exploration phase, right? And then one of the things that I was mentioning is at this point you want to go from the subsystems to components, right? So maybe here you can go a little bit to the next level. When we talk mediums, maybe you have let's say a Uber type of service, or you have tunnels, or you have school bus, right? Or I don't know, flying vehicles.
Cruise.
Right, so those are technologies that you can use to address this, right? And then when you start thinking about concept selection, you are synthesizing alternative technological approaches, which is basically what we are trying to address here. And you can have different concepts. Let's say concept 1, concept 2,
Then it could be possible to even do one of those, like a zip line.
Yeah, that could be another one, zip line.
Very tall part and then the zip line from buildings to buildings.
Yeah, I mean, I'm not shutting down any alternative. Those are options, right? The idea is that you come up with these concepts, right? Concept. Concept. And maybe these other three pieces right here are the same. The only thing that is different now for your concepts is the subsystem, and that's fine. That will make them a different concept. This guy will be using some type of Uber type of, this one, tunnels, this one, school buses, zip line. And the idea now is, based on these different concepts, how do you're synthesizing these alternative technological approaches, right? You're going to have some type of cost associated with them. Also, there'll be other measurements that you need to take into account. Maybe safety, maybe implementation. We talk about the cost, performance. In this case, how many students can you move simultaneously with each one of these options? So you start thinking about the technology that you can use to build these different concepts. And when you get to this point, concept selection, you have to get to conducting these trade-off studies among the performance, the risk, the cost, the schedule to select the preferred concept, right? So now you have these different performance metrics, risk, performance, cost, time that it's going to take you to implement this. And you start comparing, okay, between these two, which one is the best? Do all that trade-off that I think I showed you some algorithms to perform that. You can revisit some of those lectures. And then once you do that pair comparison, one of them is going to win. You compare these two, one of them is going to win. One of them is going to win. At the end, you get to select the one that provides you with the best trade-off. Maybe it's the zip lines, right? So that's the concept that you are going to move on to potentially move on to the next phase. So conducting the trade-off among this, define in terms of the components and architectures. And then you move to concept validation, which conducting system analysis and simulation to confirm that the selected concept meets the requirements and is superior to its competitors. So now you have come to the decision that, okay, this one, let me simulate maybe a computer model, computer simulation. It's going to show me that the performance is the one that I'm expecting. I'm verifying validation that process, and then I can move forward. Okay, so that's what we are trying to get at this point. We are assuming that we have different concepts. We are performing that trade-off analysis. We're selecting the concept that we think is going to give us the best performance. And then we are validating that concept, maybe using some simulation modeling. The application of this systems engineering method to this phase, concept definition phase, is summarizing, as we did for the other two phases that we had discussed already. This is a summary of the systems engineering method applied to that specific phase. I'm recording the video, I forgot. So I did that, I should have done it here, but it's okay. Questions? Mark? Okay, so the next step, functional analysis and formulation. So far, basically what we are doing is selecting best concept and moving forward. Functional analysis and formulation, keeping with the magnitude of designing a complex system. the systems engineering method divides the design task into two closely coupled steps. First is analyzing and formulating the functional design of the system, which are the actions that the system needs to perform. And then number two is selecting the most advantageous implementation of the system functions, how the actions can be best physically generated. Okay, so I'll start by looking at the definition of the component functions. The system materialization process in the concept definition phase is mainly concerned with the functional definition of the component level. So again, here we went from the system, the subsystems, and then the component level, and we can keep going down in this hierarchy. In terms of functional building blocks, we're translating the performance requirements into system functions that can be illustrated by using the concept of system functional building blocks. The following steps are involved. First, we look into identifying the functional medium. And if you remember, we have 4 different mediums that we use: signals, data, materials, energy, and force. 2 of them are if I remember correctly, there's 5 classes. Number 2 is the identification of functional elements. Operations on each of the 5 classes of media are represented by 5 or 6 basic functional elements, each performing a significant functions and found in a wide variety of system types. So this is something that we cover already, and you will see a lot of that at this point of the lecture. I'm going to be referencing back and forward some of the concepts that we learned in the first few lectures. So we talk about the medium, different type of medium. I show you a table that for each one of these basic functional elements, that could be a wide variety of types that can be used. The system action functions can be constructed from a selection of those functional building blocks. Number 3 is the relation of performance requirements to element attributes. Each functional element possesses several key performance attributes like speed, accuracy, capacity. If these can be related to the relevant system performance requirements, it confirms the correct selection of the functional element. Okay, so that's what we're trying to do, connect this with what the functional element is trying to do. And then we get to configuration of the functional elements. The functional elements selected to achieve the required performance characteristics must be interconnected and grouped into integrated subsystems. This may require adding interfaces or interfacing input-output elements to achieve this connectivity. And then 5, analysis and integration of all external interactions. The given performance requirements often leave out important interactions of the system with its operational environment. For example, external controls for energy source. These interactions need to be integrated in the total functional configuration. I'm highlighting something here. It's not advisable to attempt to optimize at this stage. Again, we are not trying to come up with the optimal design. What we are trying is to, based on what we want to achieve, based on what is available in terms of technology, how can we configure something that can help us address this problem? The initial formulation of the system functional design will need to be modified after the subsequent step of physical definition and ensuing iteration. Think I can get it. Okay, so functional interactions. So these functional elements are requiring a minimum of interconnections to other elements besides the primary inputs and outputs. However, most of them depends on external controls and sources of energy, as well as being housed or supported by a material structure. their grouping into subsystems should be such as to make each subsystem as self-sufficient as possible, right? So if you think about a car, even though they're all parts are integrated together, you know that there are certain parts that are part of a group, and there, if you disconnect one of them, that system might not work, but the car might still operate. So minimizing critical functions interactions among different subsystems has two purposes. First is to aid the system development, engineering, integration, test, maintenance, and logistics support. And two is to facilitate making future changes in the system during its operational life to upgrade its effectiveness. So if you think about a camera phone or phone with a camera, what this is trying to illustrate is by having that separation, you can easily upgrade some of these parts without interfering with the rest of the development. So here's an IDEF 0 functional model structure. This is a unique type of diagram, very simple, but very powerful. So this is a diagram method that was developed between the 1970s and the 1980s. This was developed by a professor at Texas A&M University. He has a company that only works with like Department of Energy, Department of Defense, working on developing these type of diagrams. So he's the creator of these IDEP methods. And this is something that is used worldwide. So it's a very powerful tool. It's called Integrated Definition 0. It's a primary technique for representing system functionality. The basic construct is the functional entity represented by a rectangle as shown here. So what you have here is set of functions. This is the title, let's say, of a specific component or part of your system. And then each arrow has a meaning. You have the input, the output, the controls, and the mechanisms that are used to create those controls. So this is the lower level, let's say the building block of this IDEF method. The inputs are always entered from the left, outputs exit to the right, controls, which are separated from inputs, enter the function from the top, and the mechanisms or implementation entered from the bottom. Another diagram technique is called the functional block diagram, FBD. This technique is similar to IDEF, but without the diagramming rules. Each function is represented by a rectangle. Interfaces between functions are identified by directional arrows and are labeled to represent what is being passed between the functions. When a function interfaces with an external entity, the entity is represented in some fashion like rectangle, circle, and an interface arrow is provided. So I have some examples here. So let's look at a very simple system, which is a coffee maker. And here we have identified some of the functions, and I have separated them into three groups. We have the input functions, the transformative functions, and the output functions. So again, functions are not telling you what technology you're using. It's just telling you the action. So for example, accept user command, receive coffee materials, distribute electricity, and distribute weight. These are all input functions. Transformative functions, where you have to heat the water, you have to mix the hot water with the coffee, you have to filter out the coffee grains, and then warm the brew coffee. Those are all functions. And then finally, the outputs provide status, facilitate removal of materials, and then dissipate the heat. Yes, sir.
What was this diagram technique called?
The functional block diagram?
Functional block.
Yes. So those are the input, transformative, and output functions for this coffee maker. And then if we were to build this functional block diagram for this coffee maker, there are 11 functions, and those are highlighted, well, basically in darker rectangles. So these are your functions. And as you can see, they are, as stated earlier, they are just simple. There's no a lot of information. Arrows can be connected. When you compare that to other models have specific areas for connection depending on what you're trying to do, right? The medium, the input, the outputs are all connected, but this functional block diagram is more simple. You can just connect the information as listed here, and every box is gonna represent some type of function. And then you also have 3 external entities. The user, which is here. The power source, which is here. The user is also here, and the environment. So other than the external entities, the rest of the diagram is just showing your functions. And the way they are connected is basically the route that you follow in order to complete the coffee, right? When using this system. So you start by users, receive the coffee materials, right? The user is interacting with the coffee maker, accept the user command, and from there, there's an operation that is happening simultaneously, right, with the power source. So that's distributing the electricity based on the commands. And then there's also another process here that is looking at distributing the weight. There's an environment that is impacting this this weight and the heat. And then the rest of the process is just what we know. So you have heat water, mix the water with the coffee grinds, filter out the coffee grinds, warm the brew coffee, and then you have the coffee delivered to the user. Here we have number 9, provide the status. Once that's done, facilitate the removal of the materials, dissipate the heat, and then you interact again with the environment. So yeah, another way to represent how the functions of your system are gonna be integrated. Again, here we are not showing any technology. This is not telling you what technology you're gonna be using to build your coffee maker. This is just stating the functions for your coffee maker. Since it is difficult to avoid crossing lines, several mechanisms exist to distinguish between separate interfaces. Arrows, color is probably the most prevalent, but other methods such as dashing lines are used as well. So that's what you're seeing here to make sure that you don't get confused between the interactions. In the case of power, we have simply listed the functions that require power. Notice as well that we can categorize the functions into those handling the 5 basic elements, right? So these are the elements: materials, data, signals, energy, and force. So we can separate the functions based on those 5 mediums. Excuse me. We mentioned simulation in order to make sure that this thing is performing the way it's supposed to. So the analysis of the behavior of systems that have dynamic modes of response to events occurring in their environment often require some computer-driven models that simulate such behavior. So for example, the analysis of the motion of an aircraft requires the use of simulation that embodies its kinematic characteristics. Simulation can be thought of as a form of experimental testing. How many of you have taken any classes in simulation modeling? Arena? Nobody else? No? Arena? Okay. So, yeah, that's interesting. And you guys, simulation? You guys? Okay. So that's some type of discrete event simulation. Okay. Good. So if you have not taken any simulation class, if you have built models before, any type of model basically is trying to address the same thing. Instead of experimenting with something physically, you are building a computer model and you're doing the experimentation with the model. So that's a form of testing. They're used to obtain information critical to the design process in a much shorter time and lesser cost, right? And I think cost is the main concern here, because you don't want to build something to test it, not knowing what's going to happen. Permit designer to conduct what-if experiments by making selected changes in the parameters. So the use of simulation results in scoring the candidates is generally more meaningful and persuasive than any other judgment alone. So in stating functional specifications, it's essential to quantify them insofar as might be inferred from the performance and compatibility requirements. The quantification should be considered provisional at this time. It will be iterated during the physical definition step and incorporated into the formal system functional specification document at the end of the concept definition phase. So let's do functional allocation, and then we move into discussing the exam. So functional allocation. So functional analysis is an extension of operational studies. Basically, we're trying to answer this question: is there a feasible technical approach to a system that could meet the operational objectives? At this stage, the term feasible is synonymous with possible, right? So we are trying to see, is there any way that I can achieve these goals with what we know in terms of science, in terms of technology, and so on. So feasible is basically saying I can make this happen. I'm basically worry about making sure that at least exists one way for me to achieve this goal. If there's a yes to that answer, then I'll worry about making that development the best way possible. But at least I need to start with that foundation. So here we have a diagram that is illustrating, right? So we go from input, we state our requirements. The requirements are used to define our functional analysis and allocation. We loop into the requirements analysis, and also functional analysis allows us to start looking at a design. With the design in mind, we can start looking at verification. If that's not possible, we need to go back to verify, we need to check our requirements. And once that's done, we can go back here for validation purposes. So how do we transition from the operational objectives? Remember, those are our first goals into system functions. Consider the type of media. signal, data, material, or energy that are most likely to be involved in accomplishing the various operational objectives. This association usually points to the class of subsystem that operate on the median. So for example, sensor or communication subsystems in the case of signals, computing subsystems in the case of data. It must be shown that all of the principal system functions are similar to those already demonstrated in some practical context. In identifying the top level functions that the system needs to be performing, it's important even at this early stage to visualize the entire system life cycle, including its non-operational phases. Okay, so going another layer, allocation of functions to subsystems. A simple matrix allocating subsystem to the functions may be developed. This helps to visualize or visually see which functions are being performed by none, one, or more subsystems. Right? What we don't want to see is a group of functions that are not linked to any area of your development, right? That means that your system is not going to perform as you expect. In the case of no subsystem being allocated, this represents a gap in capability, and that should be resolved. In the case of one subsystem allocated to the function, this may result in a single point of failure, right? Which could be dangerous because if that system goes down, your system will not operate. In the case of multiple subsystems that perform the same function, this may be the case of redundant subsystems or overlapping subsystem covers, which unplanned, which may be causing by conflicts if failures or different performance may elicit a different capability. So sometimes we want that duplication just to make sure that if one of these systems goes down, the system continue to operate. So if that's the case, maybe there's a subsystem that is very, very important and has some chances of going down. You want to have a backup. That's okay. It depends on the scenario that you're looking at. So this is what I was referring to, right? So you can have a list of functions for your system, and then your subsystem, and you're basically looking into whether or not you're accomplishing these functions by one of the subsystems that you have identified, like here, right? You have those subsystems. Then I will put those subsystems here, my list of functions, and then I try to identify which functions are linked to specific subsystems. So in this case, function 1 only has subsystem A allocated. Function 2 has subsystems B and C allocated, perhaps for redundancy. Function 3 has no subsystem allocated and should be reviewed and corrected, right? So that will be this function. That's not good, right? You want to make sure that you have at least one subsystem addressing that function. So let's see. This is not good. Yeah, you have to make sure that at least one subsystem is connected to this function. Subsystem A, B, C, and E are allocated to functions, but subsystem D does not have any functions. We may be a consideration for removal. So this is basically a subsystem that is doing nothing. So that could be removed. So a very simple method that can help you visualize whether or not you are going in the right direction and whether or not you are addressing all the things that needs to be addressed with the technology. One of the outputs of this step in the allocation of operational functions to individual subsystems This is important in order to set the stage for the next step, in which the basic physical building blocks components may be visualized as part of the exploration of the implementation concepts. Two important inputs to the functional allocation process are the predecessor system and the functional building blocks. So the predecessor system will be that system that is already in place, if you have any. In most cases, the functions performed by the subsystems of the predecessor system will largely carry over to the new system. So the functions maybe are not changing. What's changing is how you're going to execute them. Accordingly, the predecessor system is especially useful as a point of departure in defining a functional architecture for the new system. And since each functional building block is associated with both a set of performance characteristics and a particular type of physical component, the building blocks can be used to establish the selection and interconnection of the elementary functions and the associated components needed to provide the prescribed subsystem functions. To aid in this process for identifying those system functions, recall that functional media can be classed into four basic types: signals, data, materials, and energy, which we have discussed already. The process addresses the following series of questions. Are there operational objectives that require sensing or communications? If so, this means that signal input processing and output functions must be involved. Okay, so this is basically a way for you to rather identify the functions that your system must perform. So if you go through these questions, you start by looking, is there going to be any sensing and communication? If the answer is yes, then you for sure going to have some type of function that is going to look at signal input, processing, and output of those signals. Does the system require information to control its operations? The answer is yes. How are data generated, processed, stored, and otherwise used? So again, the data component will be involved. Does the system operation involve structures or machinery to house, support, or process materials? If so, what operations contain, support, process, or manipulate material elements? And then finally, does the system require energy to activate, move, power, or otherwise provide necessary motion or heat? If the answer is yes, so now you answer yes to all of them, then you know that you have a group of functions associated with each one of these mediums. Furthermore, functions can be divided again into three categories: input, transformative, and output. And that's what we saw for the coffee maker example, right? So we have input, transformative, and output. Input functions relate to the processes of sensing and inputting signals, data, material, and energy. Output functions relate to the processes of interpreting, displaying, synthesizing, and outputting signals, data, material, and energy out of the system. And then the transformative functions relate to the processes of transforming inputs to the outputs of the four types of functional media. So here's a diagram that is trying to illustrate what we just discussed. So for complex system, the number of transformative functions may be quite large and have successive sequences of transformations. But here we only have one transformation area, which is this one. You see the four mediums here: signal, data, material, energy. Those are serving as inputs. Those inputs are transformed. They can be transformed to something similar, or they can be transformed in combination with other mediums to something else, right? Like if you gather data from the weather, right? You're transforming that from the environment to a number, right? So that That is a signal that is being transformed to data. And so on. And then from here, we got the outputs. So in constructing an initial function list, it helps to identify the input outputs. This list directly leads the engineer to a list of input-output functions. And then the transformative functions may be easier to identify when examining them in the light of the system's inputs and outputs. So basically, start by identifying what are the inputs and the outputs that your system is going to generate, like I show you in that example for the progress report. And then from there, you start building how do you go from that to outputs.